All right, so here we have single mom births. So it says the function S gives the percentage of all births to single mothers in the US in year T from 1940 through 2000. And we're supposed to use the following information to sketch a graph of S. All right, so we have all these things we have to fulfill to make our graph. So let's go ahead and think about this. Let's get our graph started and then we can start marking points. So S is a percentage here. So this is going to be a percentage of births to single mothers. I'll put moms. And this is years since 1940. Okay, so this is going to be our 0, and out here somewhere that's going to be our 2000 because we're going to go from 1940 to 2000. And so now we're just going to kind of keep going through and see what this means. So in 1940 is about 4. How big are we going to get to? 12, 21 over 12, so 30. So maybe we'll put our 4 somewhere about here. And so we'll say that's where 4 is. And so that's where we're starting. Okay. Now it says S of t is never 0. So that means the slope is never 0. So it can't be 0. So that means we don't have, changing direction like this. We're going to go increasing and then go down to decreasing because that would give us the slope of 0. Okay. Now in 1970, we get 12. So 70, so it's about 30 years. How are we going to do this? 30 years. I might not marked this very well. We'll just call that 30 years. Okay, and that's 12. And so we'll call, this point here 12. And it's all arbitrary here because it depends on when I draw what it's going to look like. So now what? 2000, S of 2000, is going to be about 21 percentage points more than 70. Well, approximately, so I'm just going to take 21 plus 70, and I'm going to get 33. And so that's going to be up here, and we'll call that 33. Okay. And so then the average rate of change of S between 70 and 80. So 80 is going to be here. That's 40. So this is 1970. This is 1940. This is 1980. And this was the 2000. So this is 60 years. Okay. So like I said, it's not marked off good. What? That's okay. So between the 70 or where, yeah, 70 and 80. Oh, wait. Yeah, 70 and 80, that's 0.6 percentage points per year is how it's going. So, it's not going up quite large in that range from 70 to 80. So it's kind of flat there. And lines tangent to the graph of S lie below all the points between 40 and 90. Okay, so we need a 1990 here. So that's 50, that's 1990. And as you can see, that 50 and 60, maybe we should bring this over here, 60, and that's 2000. And then we can erase that part over there. All right. So between 40 and 90 and above the graph between 90 and that. So below the graph means we have to be concave up. So always when it's concave up, we're going to be below. When we're concave down, we're going to be above. So we know that there's some kind of a turning point, but we know it's not going to be a turning point where we have a slope of 0. It's just going to be kind of a gradual turning point that it's not a big one because we can't get that to be a big one. Otherwise, we'll get a slope of 0, and that's one of the reasons it says we can't have a slope of 0. So from 70 to 80, it's a 0.6 percentage points per year. It's everything below. So we're going to say, between here, that's going to disappear, so I might as well quit writing now. From here to about there is like that. And then we're going to continue on up, and it's going to go up, and then at 1990 and above is going to be kind of switching the other direction. So I'm going to have to kind of do a thing like this, and we're going to keep going up. And so we're about there. And so, it's kind of going up. We have somewhat of a turn, and then we kind of are going this direction, and we don't know what it's doing beyond that. But that's kind of a curve we can get. Again, there's not any, you know, parabolic type points where we have a slope of 0. We have this gentle curve going up, going through all the points roughly. We had the 70 was 12, and then the 2000 is about the 33. So we hit those points somehow, and it's just kind of like that. Again, rough estimates on how we get these, but that's kind of the key points we have to think about and how it works. So we had to have below for a while and above after a while. So this is going to be below, as we can see if we do a tangent here, but here it's going to be tangent like that. Okay, so I think that one looks like it should be somewhat in the correct manner. All right, so the next one here we're doing is raindrop speed. So it says the figure shows the terminal speed in meters per second of raindrops as a function of the size of the drop measured in terms of its diameter. So we're supposed to sketch a secant line connecting the points for a diameter of 1 millimeter and 5 millimeters and estimate its slope. What information does this secant line slope give? All right, so what we need to do now is we need to get out of here. Yes, we want to keep annotations. And we have to use this because now what we're going to do is we're going to have to figure out where 1 and stuff is. So I'm going to use my feature here again. It's about 5 there. And so, I'm just kind of help marking things here so I can get some ideas. Now I need my pen also here. Where's that? Let's review, start marking. And so if I want to have a pen, give me the ink. There we go. Let's do that. So here is going to be my, where's my pen? All right, there we go. So we're going to have this point here. That's 1. And now let's go ahead and stop inking. And now where did my number go? Of course, it disappeared after I got out. Okay, now is it going to disappear again? Yes. All right, so it looks like it's going to stay this time. And so what we're going to do now is we're going to move our graph so we're at the 1. So we're going to have that piece down here. So now we move this over to 1, and then we can move this down to 1 kind of to get that value here. And so now we can put our inking pen back, and we can draw that dot. And now what we can do is also insert our tangent line, or our secant line rather. So we got it through the top point. Now we'll move it so it goes to the bottom point. All right, so, well, now it didn't stay in the top point. All right, so that's going to be our secant line. And so that's connecting the points at 1 millimeter and 5 millimeter. Now we're estimating its slope. Well, now what we can do is we can kind of estimate the slope based on what the values are that we see here. And so maybe what we can do is pick 1 comma, and it's a little above 4, I think. So maybe I'll call this one 1 comma 4.1, and this one, let's see what it was. I don't remember, so let's like that one. So that's 9, 9.2 or 3 maybe. Let's say 9.2 just to be easy for subtraction. So we'll say 5, 9.2. And so what does that slope give us? So the slope is going to be equal to 9.2 minus 4.1 over 5 minus 1. And so if we plug that into our calculator, we shall get, I'm just going to do it so I don't do a mess up in my head here, 4.1 divided by 4, so that's going to be 1.275. Now, what is that? That's in meters per second per millimeter. So it's in meters per second per millimeter, okay? And so this gives us the rock, basically our average rate of change here. So this gives the A rock. Okay. For the average rate of change in the terminal speed of a raindrop as a function of the size of the drop, or we can say of diameter d. That might be a better way to do it, of diameter d, because that's what we have. And as it changes from the first one, which is 1 millimeter, to the second one, which was the 5 millimeters. Okay, and so that was our A rock. So I'm going to run out of room probably, and I don't have any more. Yeah, so what we're going to have to do is we're going to have to add some more slides here, I think. And so we'll just move that one up for now. Maybe we should copy it and put it down below this one, so we have extras just in case we need it on that one. All right, so now that's what that one gives. So that's A. So that gives us what A is. Now B, sketch a line tangent to the curve at a diameter of 4 millimeters. All right, and then what information does that give us? So we want 4 millimeters now. So that's there. And so that's that. So while we're here, let's go ahead and write what that point is. All right, so this one looks to be something like 4 comma 8 point, oh, I don't know, that's probably 9, so 8.6, 8.7, I don't know, we'll call it 8.7, I guess. It's hard to say because that's probably 9, so it's probably closer. And so we need that tangent line there, so we're going to insert a tangent line while we have that marked. And again, this is, just a guess here. So now we got to kind of come up, and then we need to bring it down. We need to come up some more, bring it down some more. And so this kind of might be a good tangent line. I don't know for sure, but it's close. So what we're going to do then is, well, actually now what we need to do is we need to come up with another point. So let's stop that. Let's come up with a point on that tangent line. So maybe we'll do 2. So if we can get that a little closer, and then we'll come down on here. And maybe that is that. So let's write what we have here. So we're going to call it 2 comma, and that's going to be 7 point, I don't know if that's 7.4 maybe. All right, so now we've got the points on here, which are the 4 8.7 and 2 7.4. So now we need that slope. And so we take 8.7 minus 7.4 over 4 minus 2. And so we get 8.7 minus 7.4 divided by 2. So that's going to be 6.65. And that's meters, or yeah, meters per second per millimeter. Okay. And so this is going to be what? Well, this is the instantaneous. Okay. So what we're doing is we're increasing. So the terminal speed now of a falling raindrop with diameter, because we based it on that diameter of 4 and millimeters, is increasing by 0.65 meters per second per millimeter. And I think that's all we need to say about that one. So that would be that. So sketch a line. What information does the slope of the line? Now estimate the derivative of the speed for a diameter of 4 millimeters and interpret the results. Okay. Well, guess what? I think that's kind of what we just did there. We kind of did sketch line well, we did B and C together, so that's kind of what that is. So that's B/C. I was looking and seeing interpret the result for that. So it gives the instantaneous, basically speed there. And so the last one then, estimate and interpret the percentage rate of change of speed for a raindrop with a diameter of 2 millimeters. All right, so what does that mean? Well, we have to come, oh, well, hey, we picked one at 2 millimeters here. So all we have to do is bring down this. Oh, that was not good. Okay, so now, there we go, bring that down to there. All right, now we need to move that over because it's not the same anymore. And so now we have the point, it looks like 2, comma, and that's going to be, if that's 7, that's less than a half, so 6.4 maybe. Okay. And now we also need to draw that secant line. And so now, or that tangent line rather, I should say. And so we're going to come up and say that looks something like that. And so now we need to pick another point on here. What are we going to do? What can we get down to 1? Does 1 work? Yeah, 1 works. And where's our line? There it is. Too many lines on the table now. Now let's see if we can arrow down to get it a little bit closer. All right. So that looks like we have, that's 5 there, maybe 4.8. So 1 4.8. All right. So now we have to remember those two so we don't mess up. And so we need to find the slope of that. So we'll take 6.4 minus, we said 4.8, and then that's just going to give us our slope, which is going to be 1.6. So let's go ahead and go over to the next page. And so for D, that was 1.6 millimeters per second per millimeter. Okay. And so now what we had to do is now we want the percent rate of change, I believe is what they asked for, estimate the percent rate of change. And remember, that's going to be equal to the previous thing, the IROC, which is this is, or the derivative, I mean, that's the f prime of x or whatever our function is. So it's the 1.6 divided by, and what did we have for the thing? It was 6.4, I believe. And then we take that times 100. And so we have 1.6 divided by 6.4 times 100. So we get roughly 25%, it looks like. Okay. So that's a nice number. So that probably is what they had in mind. And so what does this say? Well, it says the terminal speed of, what was it, falling raindrop with, now we were at diameter 2 millimeters, is increasing, this is 2.5% per millimeter, increasing by 25% per millimeter, okay, at that 2 millimeter diameter, okay? So that would be what we need for the percent rate of change. First, we had to get our f prime, which is the tangent line at that 2. Then we divided by the y value at 2 times 100%, got our 25% per millimeter, and then we wrote and interpreted what we found. All right, what about this last one here? So we have a balance and savings account as shown below. Estimate how rapidly the balance is growing 10 years after the initial deposit. Estimate the percent rate of change 10 years after the initial deposit. All right, so let's go where 10 years is. Okay, just barely long enough, that works. and barely long enough here too. All right, so I'm going to say that's good enough. So now we need our pin again, and we need to come up with what is that point. So I'm going to call that point 10 comma, okay, well that's 23, and I don't know, it could be 22. It's not quite half, 2240 maybe. Okay. And these aren't lined up quite right either. So, this could be moved over, which would move that one up. But this is where we're going with. We're going with 2240. And then what we need to do is we need to draw a tangent at that point. So we need to draw our line. And so maybe that looks close. I don't know. And so if we go up a little bit more, that might be about as good as we're going to get. So we have have that point. So now let's choose another one. Let's do 6. I don't know why, just because it is there. And so then we have to find our next y. So we go down. That looks about there. And so now let's go ahead and ink that. And so that looks to be 6 comma 1880 maybe. Who knows? Close. Anyway, so what is our slope going to be? Our slope, which is equal to f prime of, it doesn't say what our thing is, maybe y or t or something, is going to be equal to the 2240 minus the 1880 over 10 minus 6. And so that's going to be 2240 minus 1880 divided by the 4, so that's going to be 90. And so we get 90 what dollars, and then per year. Okay, so that is our slope at that tangent line. Now we need the percent rock. Okay, so it doesn't say, do any interpret the results. It just says find these values. So we're not interpreting now, we're just finding them. So now that's going to be the 90 over the value at that point, which is 2240, and then times 100%. And so that's going to be divided by 2240 times 100. So that's going to give us about 4.02%. Okay, and that's per year. And that's going to give us our value, and that's going to be all we need to do on that one. And that's all I have for this one. So hopefully that will help.